In this video, we're going to prove the famous ratio test, which basically says that if you have any series with just positive terms and the limit of the ratio a sub n plus 1 over a sub n is equal to L, then if L is less than 1, that is, if this limit is less than 1, the series converges. If L is bigger than 1, the series diverges. And if L equals 1, try another test. The ratio test was inconclusive. And we'll prove each of those ABCs one at a time. The proof of A. Suppose the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to L, which is less than 1. Clearly, there exists an R in the real numbers such that L is less than R, which is less than 1. Between 1 and L, you can always find a number in between. For example, L plus 1 over 2 is in between, strictly in between L and 1. So there does exist this R. Now, since all of these terms are approaching L, now here's a number line. Here's L, here's R, and here's 1. At some point, all of these terms are going to be so close to L that all the terms are going to be less than R. For n large enough, that ratio will be less than R. A sub n plus 1 over a sub n will be strictly less than R. Okay. Suppose that, meaning this, is true for n bigger than capital N. So when n is bigger than capital N, all of the terms are going to be less than R. Okay. Assuming n is bigger than n, we have a sub n plus 1 over a sub n is less than R. That is, a sub n plus 1 is less than R times a sub n. Then a sub n plus 2 will be less than R times a sub n plus 1. But a sub n plus 1, well, there's this R. A sub n plus 1 is less than R times a sub n. Now, a sub n plus 3 is less than R times a sub n plus 2. Well, that is R times, that's going to be less than R times anything less than a sub n plus 2. And a sub n plus 2 is less than that, R squared a sub n, also known as R cubed a sub n. In general, a sub n plus k is less than Now notice, when it was 3, we had r cubed. When it was 2, we had r squared. When it was 1, we had r to the 1. This is less than r to the k times a sub n. This is always true. Okay, and this is where we have the problem or the proof. The summation of a sub n plus k, as k goes from 1 to infinity, this is less than the summation of r sub k times a sub n as k goes from 1 to infinity. But the a sub n is a constant. It can come out in front. So we have times the summation as k goes from 1 to infinity of r sub k. But this is a geometric series, and r in absolute value is less than 1. R is positive, and it's less than 1. That was one of the big premises, is that R was less than 1 and bigger than L, which is positive. After all, how can these ratios of positive numbers be anything but positive? So this converges. So this equals a sub n times a convergent series. It converges. The product converges. A sub n is just some positive number. Okay, and remember what happened. So you don't have to write this for the proof. 1 to infinity. This is the same as the summation as n goes from 1 little n up to n minus 1 plus the summation of this. The summation of a sub n, well, I guess this should go up to capital N. A sub n plus k, where k is 1 to infinity. So I'm adding up all the subscripts from 1 to capital N, just like I'm adding up here, but I'm adding more over there. And then I pick up at n plus 1 and I go to infinity, just like we have there. Okay, this always converges. It always converges. You're just adding up capital N positive integers. It's going to add up to a finite value. And this also converges. So the whole thing converges. And that completes part A. Now, part B. Proof of not part 2, but part B. Okay. Suppose the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to L, which is bigger than 1. So in terms of a number line, we have 1. L is bigger, and I'm going to pick an R in between. Then there exists an R in the real numbers such that 1 is less than R, which is less than L. Now, like before, these ratios, that's a series on its own. It's convergent to L. At some point, 1, R, and L, all of these are fractions will be in a neighborhood around L that are all its values are bigger than R. There exists in N such that whenever N is bigger than capital N, A sub N plus 1 over A sub N is bigger than R. That is, A sub N plus 1 is bigger than R times A sub N. Like before, let me just be clear for N bigger than N. Hence, if N is bigger than N, we have that A sub N plus K is bigger than R to the K times A sub N. And I guess there's no need for me to say this. Okay, that statement is just going to be true. Which is extremely powerful statement. This is an extremely powerful statement. Because now we have that it's going to diverge. Then the summation of A sub N plus, this is for all K bigger than or equal to 1. So the summation of A sub N plus K, as K goes from 1 to infinity, that is the summation of all of those, is going to be bigger than the summation of all of those. Bigger than the summation as K goes from 1 to infinity of A sub N R to the K, which diverges since R is bigger than 1. That's the proof of part B. Now, part C, I guess I can do part C like this. Part C. This is when the limit equals 1. Okay, so the summation as n goes from 1 to infinity of 1 over n, and the summation as n goes from 1 to infinity of 1 over 2. Well, let's just write consider. Consider those. Okay, now the limit as n goes to infinity of that ratio, 1 over n plus 1 divided by 1 over n, which is the limit as n goes to infinity of n over n plus 1 equals 1. And the limit as n goes to infinity using that sequence, 1 over n plus 1 squared divided by 1 over n squared. This is the limit as n goes to infinity of n squared over n plus 1 squared, which is 1. Okay, so we have two ratios. We have two series, and their ratios give us 1. Okay, that doesn't mean that the test is inconclusive, but here's the problem. The summation of 1 over n and then goes from 1 to infinity diverges, and the summation n 1 to infinity of 1 over n squared converges. That is the limit of the ratio when it equals 1. It's inconclusive. So sometimes it diverges, sometimes it converges. Hence, the ratio test fails when L equals 1. That is, the test is inconclusive. You didn't learn any information other than the fact that the limit of the ratio was 1. You didn't determine whether or not the series converges or diverges. This completes the proof for the ratio test. As always, if you like this type of mathematics, where we do nothing but proofs, subscribe to the channel. Leave a comment if you hate proofs, if you love proofs, if you're new to proofs, if you need help with proofs, if you would like to see a proof that I haven't made up a video for, ask. If you have any comments, leave a comment. Let me know what you think about what I'm doing. Most of all, watch and learn.